Hello and welcome to the first workshop for ME 474 using Abaqus. This is using Abaqus version 2016. If you're using a slightly different version, perhaps some of the buttons may look different or may be located in a slightly different spot. However, the material and the method used here should be relatively the same. So this is also going to be using the student edition. So if you're using any edition, really, you should be able to follow along and use this same workshop. So here is the intended problem to solve. We're going to use just some very simple truss elements actually to solve this problem. We just want to look at the compressive, or in this case tensile loads, and see how much we can extend this little bar using loads P1 and P2. So we will refer back to this diagram and this problem statement several times throughout the workshop. But essentially we have two different loads. P1 is 525 kilonewtons, P2 is 175 kilonewtons. We have three different lengths for each one of the bars. We've got a length of AB equal to 300 millimeters, BC is 350 millimeters, CD is 250 millimeters, and we've got two different cross-sectional areas to deal with. The top two portions of the bar there from A to C, they have a cross-sectional area of 900 millimeters square, and the lower portion of the bar from C to D has a cross-sectional area of 450 millimeters squared. Then we also have some radii that we can use if we wanted to actually model these as full circles. The modulus for the material that we've chosen is 70 gigapascals, so we're modeling something like an aluminum, and perhaps we'll choose a Poisson's ratio equal to 0.3, although it's not shown on here. And if we actually went through and just calculated using very basic mechanics of materials, we would find that the solution to this problem should say that point D moves by roughly 5.7 millimeters. So that's going to be what we're hoping to find from our model. If we take a look at the other part of the workshop that I've got listed here, we need to keep in mind that Abaqus itself does not keep track of units for you. So it's important that you keep track of your own units. And we're going to be working in this metric in terms of millimeters. So we're going to have a length in millimeters. Loads need to be input in terms of newtons. And our modulus values are going to be in megapascals. So that's going to be important as we go through and solve this problem. So again, here's what our problem statement looks like. Let's go ahead and fire up Abaqus 2016 Student Edition. We're going to start off by creating just a standard/explicit model. Here's what our interface looks like. So the first step, using our part module, we are going to go ahead and create the first part, and I'm intending to show you how to do this three different ways. The first way, which is a bit longer, but maybe the more intuitive way that you would think of to do it, is we're going to just create three different parts, and we will assemble them and connect them together and then apply our loads. I'll also try to show you a slightly faster way perhaps, where we do it all using just one part and we assign some different section properties. So for the first part, we're going to call this one AB. So this will be representing the section from point A to point B. We're going to be modeling these as a wire section, so all we're going to have to do is just draw straight lines. And for an approximate size, we know we're going to be having some slightly longer lengths since we're doing this in millimeters, so perhaps we'll put in an approximate size of 1,000. If you don't change that, it's not a big deal. It just means that when you go to draw it, you may actually end up going off of the grid that they show here on the screen. So if we refer back again to the problem, section AB needs to have a length of 300 millimeters. So we'll go ahead and we'll draw our first point using the Create Lines tool. And you'll see in the dialog box down here at the bottom that Abaqus asks you to pick a starting point for the line. So we will start at 0, 0. And we're going to draw our straight line going down. And once again, we need it to have a length of 300. So if we're starting at 0, 0, we're going to go to a value of 0, comma, negative 300. so that we draw a line going straight down. If we want to be able to zoom so we can see the whole thing, we can click on this button up here at the top, the Auto Fit View button, and now we can see we just have a straight line. We're done drawing that line, so we'll click on the little X here to exit out of that tool. And this is the only part that we needed to draw, or the only line we needed to draw for this part. So we'll now say that we are done. And there's our first part, part AB. So now we're going to do that 2 more times. We're going to draw part BC and part CD. So for part BC, we need to have a length of 350 millimeters. So let's go ahead back. We're going to call this one BC. It automatically defaults to being a wire with an approximate size of 1,000, so that fits well. And for this one, we're going to draw this section again. We're going to use our line tool. We're going to start out at 0, 0, and we're going to go to 0, negative 350. So that way we've got a line now at a length of 350. And again, if we want to see the whole line, we can resize the window so that now I can see my whole line. We'll click on the X because we're done drawing. And we're done drawing that section, so we say done. And last, we're going to draw our portion CD, which has a length of 250 millimeters. So we'll come back, we'll create one more part, part CD. Again, it's a deformable wire, size of 1,000 is fine. We're going to start out using our line tool again from 0, 0, and this time we'll go to 0, negative 250 to get a line of a length of 250. We're done drawing the line, and we're done with our sketch. So now at this point, if we look over here on the tree, I should have 3 parts, part AB, part BC, and part CD. So at this point, we're all done creating the different parts that we need. Next, we'll come in here and create the properties that we need. So we'll change our module now down to the property module. And if we recall back to our problem statement, we had a modulus of 70 gigapascals, and I said that we could use a Poisson's ratio of something on the order of 0.3. You'll see for these sections it really isn't going to have a great impact on our problem. So in order to do that, we're going to create our material, which is the very first button here, Create Material. When I click on this, we'll call it aluminum. And the only things we need to define are down here under the Mechanical tab. We go to Elasticity and Elastic. And that brings up our little field here where we need to define Young's modulus and Poisson's ratio. So again, the problem statement said to use 70 gigapascals. Now if you recall back to the slide I showed with the unit consistency, that one indicated that if we're working in millimeters, our modulus value needs to be in megapascals. So we need to use 70,000 megapascals to keep consistent. And for a Poisson's ratio, we'll use 0.3. Okay, so that's all we need for this particular problem for our material. So we'll say OK. And now over here in the tree, I can see that I've got one material called aluminum. The next thing that we're going to do is we're going to define 3 different sections. One section to represent AB, one section to represent BC, and one section to represent CD. Now we can take a little shortcut here because the only thing that's going to change over these sections is the cross-sectional areas. Since the material stays the same throughout, A, B, and BC have the same cross-sectional area. So we'll reduce this down to just create 2 sections. One section will be AC, and one will be CD, where we can define different cross-sectional areas. So for A to C, we have a cross-sectional area of 900 millimeters squared. So let's come back to our tool. We're going to click on the Create Section. We're going to call this one Section AC, and we're going to use a beam truss type of section assignment. This is because we're not really interested in any bending. We're just interested in straight tension or compression. In this case, it's all in tension. But we're not really interested in adding any terms related to bending, since all the loads are being applied in the axial direction. So we're going to be creating truss elements here. So we'll say Continue. The next question that's asked is what material are you using? So we've only created one material, so it shows up here by default. If we had created multiple materials, we can use this drop down here to select the material that we are interested in. And the second block here asks you for a cross-sectional area. So this is where they're going to be different depending on the different sections that we're looking at. So for section AC, we have a cross-sectional area of 900 millimeters squared. So we're working in millimeters, so we need to continue working in millimeters to allow Abaqus to solve this using consistent units. So we'll say OK. We've now created our first section. So if we open up this block here, we can see that we've got one section called AC. If I continue and do that one additional time now, I'll create another section. This one is going to be called section CD. By default, it still has a truss type up, so that's good. My material stays the same. And for this section, we have a cross-sectional area of 450 millimeters squared. So we'll say OK. And now I've got both of my sections. So we're not quite done yet, and this is a part that's frequently missed. We also need to now actually assign those sections to the individual parts. So using the drop downs here across the top, let's go ahead and bring up part AB. And we're going to click on this third button down that says Assign Section. And the prompt down at the bottom says select the regions to be assigned a section. So I will go ahead and click on the whole part. And I'll say Done. And then this drop down up here shows up asking me to select which section we want to assign. So part AB is going to fall in that first section AC. So I'll select that and say OK. Now I can change my part drop down to BC, and we'll repeat those same steps. So I'm going to assign a section. I'm going to click on the whole part. I'll say Done. And in my drop down here for sections, again, I'm going to select AC because BC is part of that section. Okay, so I'll say OK. And we do it one more time with part CD. I'm going to click on Assign Section. I'm going to choose the part. I'll say Done. And in my drop down, I'm going to choose section CD since this is the appropriate properties for that section. So now I'll say OK, and we've assigned section properties to all three of those parts. So that completes everything that I need to do here for the property module. We'll move on down now to the assembly module where I need to bring in all three of my parts and assemble them accordingly. So I'll start off here by using the Create Instance button. I want to end up with an instance of all three parts, so I'll highlight all three of them. As far as whether they are dependent or independent, we can actually, it doesn't really make too much of a difference in our case. It might be a little bit easier for us to just say independent so that we can mesh at the assembly level. If you choose dependent and you mesh at the part level, that's okay too. It just means we have a couple of extra steps in there where we would need to mesh them one at a time. I also want to make sure I choose this button down here, Auto Offset from the other instances. That way it's easy for me to tell where the three lines are, and I can line them up and stack them in one long straight line. If you don't choose that, so if I turn that back off here, you'll see that they're all just stacked on top of each other, and it may be difficult for you to click on the appropriate part when you go to try to move them. So let's use our auto offset here so that way it's easier to click on parts individually. So now I'll say OK, and I've got all three parts now in my assembly. But I want to orient them so that they're all stacked up to create one long part. So in order to do that, I need to click on the Translate Instance button. And we'll see that Abaqus says select the instances to translate. So I'm going to click on my second one here, which is the longer part. So I can tell right away just from the lengths that this is AB, this is BC, and this is CD. If it wasn't so obvious, I can also use this pop-up box down here in the bottom right that says Instances, and I could click on BC, and it'll highlight that for me in the screen, and I'll say OK. And now Abaqus asks me to select a starting point for the translation vector, or I can enter some coordinates. So for this particular problem, I really just want to move the top of BC to be in contact with the bottom of AB. So I can click on this point, the top of BC, and I'll click on the bottom of AB, and that'll move it so that those two lines are now aligned with each other. If that looks okay, you can say OK. And now I've created a slightly longer straight line. If I want to be able to see it all, again, I have that same auto fit button here at the top. I can click on that, and I can now easily see that I've got my two parts here lined up. I'll do the same thing for CD, so I'm going to click on Translate Instance. I will once again use the instances pop-up here just to make life easier. I'll click on CD and say OK. And now I want to move from the top of CD down to the bottom of BC. And as long as that looks okay, I'll say OK. And now when I zoom out, I've got one nice long straight line with my three different pieces that I can highlight here. Okay, so at this point the assembly is now complete. I can change my module to the next part, which is step. For this particular case, this will be a fairly straightforward problem to solve, so we're going to click on Create Step. We always need at least one step. By default, there's the initial step where you can put in boundary conditions, but if we want to apply any loads, we're going to need to create a new step. So we're going to call this one Load, and we'll accept the defaults here, which is a general static step. So we're not doing anything dynamic in this problem. There's no temperature effects, so we're just going to keep it here at a general static step. You can enter in a description if you so desire. For our particular problem, we can actually just accept all the defaults here. There's lots of different options that you can choose from, and as you get into some more complicated problems, perhaps you'll have a need to use some of these functions. But for this fairly simple problem, we're going to just go ahead and accept the default values here. So we'll say OK. And now we've got an additional step. So if I look over here in my drop-downs, in my tree, I can see under steps I've got initial, and now I've got this load step that I just created. Okay, so at this point the step module is complete. I can change my module now to interactions, and in this module we can apply things like contact or various different constraints. So in my case, we would like to be able to create a constraint where we can tie together nodes from one part to the next part. So in order to do that, it might be easier if we have sets where we have defined the top and the bottom of these different components, so that way we can more easily choose them. So we're going to go ahead and change the module here back to part, and we'll start off with the first part, AB. So we'll change our drop down here to say AB, and over here on the tree I can open up AB as well so that I can see all the things that are inside here already. And if I double click on sets, I can create a new set, which I will first call top. So we will we'll create a set for the top and the bottom of each one of our parts. So I'll call this one top. Click on continue. You'll see the dialog down here at the bottom says select the geometry for the set. I'm going to click on the very top here and I'll say done. And now I can see at the bottom it says the set top has been created with one vertex. I'm going to do the same step again. I'll double click on sets. This one I'll call bottom. I'll say continue. And I just click on that bottom point and I'm going to say done. And so now I've created a set with the bottom point as well. I'm going to go ahead and change the part to BC. In my tree over here I'm going to do the same thing, BC. This same feature can be found up here under Tools, Sets, and I can do Create. I'll call this one again Top. Say Continue. Click on the top point and say Done. Go up to Tools, Sets, Create. I'll do one for the bottom. And we'll click on the bottom again. Done. And now I need to do the same thing for part CD. So I'll change that part to CD. We'll go up to Tools, Set, Create. We'll call this one Top. Click up here at the top. Say Done. And one last time, Tools, Set, Create. Call this one the bottom. And once again, we'll click on that bottom node. So we'll say we're done. And now we've got a set on each part representing the top and the bottom of those lines. So let's go back to that interaction module. The function that we're going to be using here is under create constraint, and we're going to be using the tie constraint. So what tie does is it assumes that any nodes or surfaces or faces, whatever you have, are going to be perfectly glued together so that all of the nodes will move together as one. So in our case, that's what we'd like to do. We'd like to have it so that this bar behaves as if A, B, B, C, and C, D are perfectly connected. So we're going to use the tie constraint. And for the first one, we'll call it AC, because what we're going to do here is we're going to tie together AB and BC. So we're going to end up creating AC. So you can call it whatever you want. You can call it something different if you'd like. So I'll say continue. And now Abaqus asks you to choose what is the master type. So you can either use surfaces or nodes. So we're going to use a node. And now it asks you to select the points for the master nodes. Or over here on the far right, you'll see there's a box where we can select sets. So if I click on that, it brings up my dialog box here, and I can see a list of all the different sets that we've created. So if I want to easily select the bottom of AB and the top of BC, I can also turn on this highlight sections in viewpoint so that way we can see it. But I'm first going to choose the bottom of AB, so I can see on my screen that highlights this point. That's the point I wanted. And I'll say continue. And now it asks me for the slave type. And again, I'm going to say it's another node. And it automatically brings up this dialog box again. And I now need the top of BC. So you'll see it's the same point again. I'll say continue. And now it brings up this constraint dialog box so I can see which points I've chosen. There are some things that we can change if you so desire, but for our purposes we're going to go ahead and accept the default values here. So we're going to say OK, and we'll see this little circle shows up here on the screen indicating that we have created a tie constraint. So we're going to go ahead and do the same thing now and tie together the bottom of BC and the top of CD. So we're going to create another constraint. This one we can call it BD then, because it's going to create the connection from B all the way through D. It's still a tie. We have another node region, except now we're going to choose the bottom of BC. And it's another node region, and we'll choose the top of CD. So it's the same steps we just went through. We'll go ahead and accept the defaults, and we'll see that we've created another constraint here at that location. Okay. So now we've created two different ties. So now this bar should act all as one. And that's it for the interactions for this problem. So the next thing that we'll do is we'll create our load module. So we'll change module here to load. And what we can do in this module is create loads as well as create boundary conditions. So we need to fix the very top. If we go back and look at our problem statement, node A is tied to the wall up here, so it's going to be perfectly fixed to that wall. All the rest of the nodes are allowed to move, but then we need to apply a load at point B and a load at point D. So we've got both boundary conditions and loads that we need to apply. So let's start out here by creating a boundary condition, and we can put this one in the initial step, since that's where I usually put most of my boundary conditions, and we'll call this one fix because we're going to fix node A. So we can either do that by creating displacement and rotation boundary conditions, or we can use this function over here at the end, the encast function, which will go ahead and lock the motion in all directions. It actually goes a little bit above and beyond what we need for a truss element, but Abaqus will automatically turn off any boundary conditions that don't apply. So we'll say continue. And in this case, we are looking at the top of AB. If that didn't automatically pop up, that box should appear down here in the lower right for sets, or in this case you could just click on that node at the very top and get the same effect. So I will choose the top of AB, and I'm going to use this function down here at the bottom, which shows you that U1, U2, and U3 are all equal to 0, so that's displacement in the X, Y, and Z direction, as well as rotations about X, Y, and Z. So everything is equal to 0. So in our particular case, again, some of those boundary conditions don't apply with a truss element. However, Abaqus will just automatically ignore any that don't apply. So we'll say OK. And at this point, we can see now that we have locked that node in every direction. The other thing that we needed to do was we needed to apply a load at point B and a load at point D. And when we look at our problem statement, the load at point B has a magnitude of 525 kilonewtons. If you recall from our unit consistency, we need to be working in newtons, so we'll have to enter 525,000 newtons at node B. So let's go ahead back to our Abaqus. We will say create load. You'll notice that in the initial step you can't apply any loads, so we need to change this to the load step. It is mechanical. It is a concentrated force. Let's give it a name here of point B. Okay, so that way we know where we're applying it. We'll say continue. And again, it automatically brings up my sets dialog box just because I've been using this. If you haven't been using it, it's available again down here in the lower right. Or again, you could just click on the screen in this case, since it doesn't actually matter whether we're applying it to the bottom of AB or the top of BC, since those two nodes are now perfectly tied together. So in our case, I'm going to say bottom of AB, since that is the same, that's point B. We'll say continue. And we're applying our load in the to direction, which is the Y direction. And we want it to go in the negative direction, so we need negative 525,000. And if I say OK, I will now see that there's an arrow on there and it's pointing down, so I can verify that it's pointing in the right direction. If I had typed in a positive load here, you would see that the arrow is pointing up. I'm going to do the same thing now at point D. That one has a force down here, which is load 2, equal to 175 kilonewtons, so I need 175,000 newtons. So again, we will click on create load. It's a, we'll call this one point D. It's a concentrated force, so we'll say continue. I'm going to put it at the bottom of CD. That's my point right there. And again, we're still going in the to direction. It's negative 175,000. I'll say OK. If I fit this to the window or zoom out a little bit, I can see that I've got my arrow pointing down at that location as well. So now I've got my boundary conditions, I've got my load set up. We are all done with the load module. I'm going to change this now to the mesh module. Since we are working as a where everything is an independent, we can actually mesh then at the assembly level. And ideally in this case, since we're not looking at buckling, I don't want anything to bend. I really just want one element on each one of these parts, so that way the only thing it can do is move where those nodes are. I'm not really interested in anything else. I just want to stretch it. So that's what I'm going to go ahead and do. I can achieve that by either meshing this with a global part, as global seeds, or I can come in here and say seed edges. And I'm going to go ahead and dismiss this window. So Abaqus asks me to select the regions to be assigned. I can just choose the whole thing, say done. And if I do this by number, I can say that I really just want one element on each one of these parts. So if I say apply and say OK, I can see each one of these little magenta boxes represents where a node is going to be. So I'm going to end up with an element here, an element here, and an element here. So I'm just going to have 3 elements. That's really all I need for this problem, since I'm not considering bending. The other thing I do need to do, though, is check what types of elements it's going to use. So that's the 4th button down here, assign element type. And now Abaqus asks me to select the regions to assign these element types. I'm going to choose the whole problem and say done. And by default, since I've been using wires, Abaqus chooses beam elements. But I had assigned truss sections, so I actually need to change this to say truss, so that way Abaqus is able to properly solve it. If I didn't do this, what ends up happening is we've got a mismatch between the section that I assigned and the element types that I'm using. And in that case, then Abaqus will actually crash and give you an error message that it's missing section assignments. So I can now say OK, I've assigned truss elements. And the last step here is to mesh the part. And it says select the part instances to be meshed. I'm going to select the whole part, the whole model, and I'll say done. and now that's it. It tells me that I've got one element generated on AB, one element on BC, and one element on CD. So I've got 3 total elements. The optimization module we don't really use in this class, so the next step is the job module. This is pretty straightforward. We're going to go ahead and create a job. I'll call that job Workshop 1 for our first workshop. I only have one model in my CAE file right now. It's called Model 1. So I'll say Continue. I can go ahead and select or just take all the defaults here. For the most part, a lot of these functions in here are aimed at if you are using a computer cluster with multiple processors, or you want to try to schedule your job for a future time. For the student edition and for just running it locally, we don't really need to worry about any of those things. So we'll go ahead and say OK. And now to actually run the job, what I think is the easiest way is to open up the Job Manager, which is right next to that Create Jobs button. I'll see a list of all the jobs that we've created. So far it's just one job. And if I want to run that job, I can click now on Submit. And it says that I've already got some files created for it. I must have called a job earlier, Workshop number 1. So I'll say OK. And I'll see that now it says Submitted. And Abaqus is thinking a little bit about it. If I want to try to watch what's happening here, I can click on Monitor. That'll bring up this little pop-up box here where I can see if there are any error messages or warnings that are appearing. And right now I can see that it's running. I can see that Abaqus started. It completed the initial steps. It started running Abaqus Standard, completed Abaqus Standard, and the job finished just now. And I'll see in my window up here that indeed it appears that everything ran just fine. I can say Dismiss. I'll see back in my Job Manager that it says the job is completed. So now if I want to look at the results, I can click on the Results button. And by default, Abaqus brings in the undeformed shape. If I click on this button here, which says Plot Deformed Shape, I can see that my beam has in fact expanded. You'll also note down here in the bottom it shows that it's been scaled roughly 16 times just for visual purposes so that I can see that something happened. There are ways of adjusting all those things if you'd like. However, for this module it's not really all that important. What I am interested in looking at is what the total deflection is, or the total displacement. So if I click on this Contours button, first Abaqus is showing you just the Mises stress, but I'm really interested in displacement. So I'm going to come up here to the top where right now there's the letter S for stress. If I change that to U for displacement, I can now see that Abaqus is displaying for me what the total displacement is for this problem. This is the magnitude, which theoretically then combines X, Y, and Z, although it should only be moving in the Y direction. I can change that to only show U2, so that way it's only displaying my deflection in the Y direction. And I'll see at the very bottom, again we're working in millimeters, it says that that node has displaced 5.694 millimeters. If we go back to our problem statement, I said that if you just use simple engineering mechanics, solved it by hand, you would find that the answer should be 5.69 millimeters. So I would say that we can feel pretty confident that we have successfully modeled this problem using these basic truss elements and our simple material properties. So there you have it. That's workshop number 1 for our ME 474 class. Hopefully that was fairly explanatory for you. And if you have any questions, please feel free to bring them up in the next class.